Welcome to video on the 555 timer IC. In this video we will have a look at the applications of a 555, the working principle of a 555, the monostable, the astable since these are part of a syllabus, then do a problem and some simulations. So the 555 can be used for timing applications from microseconds to hours. You can max out this timer circuit. Okay, it can have adjustable monostable operation. You can have it connected as astable, a monostable, even with adjustable duty cycle for the astable. With the circuit, you can do missing pulse detections, pulse width modulation, pulse position modulation, sequential timers, so multiple 555s triggering each other, and then triangle wave generation if you connect the integrator to a 555 timer. But the two that we will be focusing on is the astable and monostable. So first, the working principle of a 555. My theory is that if you understand a component and how it works, you can do anything with it. You don't have to read off equations from a data sheet. You can basically plan or build your own circuits without any external sources. Okay, so if we have a look at the 555 here, we have two comparators, a transistor with a resistor connected to our RS latch here, and our RS latch has a reset. So 555 is 8-pin chip. So we have VCC, ground, reset, output, a threshold, this pin called CV, which is just a connection to this voltage divider here, and the trigger. Okay, internally we have 3 equal resistors from VCC to ground. So on here, VCC divided by 3 and 2 times VCC over 3. Okay, so the threshold is to detect when we breach 2 times VCC over 3, and the trigger is connected to VCC over 3. Right, then this pin here called discharge is typically connected to the capacitor to discharge it, so creating either a path to ground for a discharge, or it can be at high impedance, so basically there is nothing here. Reset is when you need to force this timer into a reset state. Okay. Output is typically where we will be seeing our waveform. Okay, so everything around here is around these two comparators and this RS latch. So the truth table for RS latch, if both are 0, it remains in the previous state. If R is 1, we go to a reset state. So Q naught becomes 1. Okay, so this is a high into a resistor and switches on this transistor here. So basically, our discharge becomes a ground if we neglect the resistance of this transistor. And if S is triggered, we are setting our output basically. So Q is out, so our output will become 1, R becomes 0, so here we will have a high, this will be a 0, so this transistor will be off and a high impedance, and the state 1 1 is forbidden for RS latch. Okay, so looking at the comparators, VR, okay, so VR is what's going into the reset, is the gain of an op amp, which is infinite, and we have threshold minus 2 times VCC over 3. And for the set, it's VCC over 3 minus the trigger. So whenever one of these breaches a threshold, the output will either be a high or a low. So either a 1 or a 0 going into the RS. Okay, so VR will be a high when the threshold is greater than 2 times VCC over 3, and VR will be a low when the threshold is smaller than 2 times VCC over 3. So this is to trigger a discharge or a reset. So when VR goes high, we are forcing a reset. So basically, discharge becomes a ground and the output becomes a 0. To force a set, we have our trigger. So whenever the trigger is lower than VCC over 3, our VS will be high and our output will be triggered to be on. And our discharging will be off, will be a high impedance. Same with a low. Okay, so as I said, everything is around the two comparators and this RS latch. So for monostable operation, we typically connect our threshold and our discharge together to a capacitor with a resistor to VCC. So this capacitor will be charging towards VCC when it's on. Okay, and our trigger input is here on our comparator. So basically we will assume that the circuit is in a reset state and the capacitor is discharged. Okay, reset state means that this is a 1 and this is a 0. So the voltage there should be at 0. Right. Okay. Pulling the trigger low, S will become a 1. Our output will become a high and our discharge will become a high impedance. Okay, so pulling the trigger low, so inputting a pulse, will ensure that this becomes a 1 and this becomes a 0, and basically this becomes a high impedance. So theoretically, there is infinite impedance looking this way and infinite impedance looking that way, meaning our capacitor can start charging from 0 volts to VCC. Right. On its way to VCC, it will reach the threshold here, which is VCC, 2 times VCC over 3. So it's charging towards VCC, so that is V infinite. It's charging from 0, so that is V0 plus. And at 2 times VCC over 3 is our time t. Right. So basically, tau is our RC constant. And if we plug in everything that we just said, our output or our capacitor charging will be 2 times VCC over 3 at time t, charging towards VCC starting from 0 and making t stand alone, we end up with 1.1 times RC. Alright, so that is how we design the monostable. Connect it correct, pick a value for R, pick a value for C, and the constant being used is 1.1. Right, so here is the diagrams. So the moment you pull the trigger low, the output will become high and the capacitor will start charging towards our limit here until it reaches 2 times VCC over 3, and then the output is switched off and the capacitor is discharged again. That is how the monostable works. The astable is when we connect the trigger and the threshold together and place it at the capacitor. Okay, and the discharge is here between a resistor voltage divider. So when this discharge is on, so when this is a ground, our capacitor will discharge through RB towards ground. And when the discharge is high impedance, our capacitor will charge towards VCC. Okay, but every time there is the two triggers in between, so our capacitor voltage will be kept between 2 times VCC over 3 and a third of VCC as it is. So, okay, let's get rid of all of this and let's look at the states. So assuming that the circuit is in a reset state, so the output is low and discharge is ground. Okay, so the capacitor will discharge towards V infinite, which is 0, from 2 times VCC over 3. Okay, so assuming that our capacitor stays within these two limits, it will be 2 times VCC over 3 while it's discharging towards ground, and while it's charging towards VCC, it will start from a third VCC. Okay, so charging from 0 towards 2 times VCC over 3. The trigger will happen at VCC over 3. Okay, so we want to know what is the time spent charging from 2 times VCC over 3 and our trigger. Okay, this is the initial stages. Okay, when it started off from 0. Any case, so this will be an ongoing process. Let me show you the diagram before we get to the maths. So when the output is high, our capacitor is technically charging. And this happens between these two limits. So it will charge towards VCC and it will discharge towards 0. And there will be a time connected to each one of these. So time spent high and the time spent low, and the sum is the total time. Okay, so the high time is when we trigger at 2 times VCC over 3. Okay, so up here. The low time is when we trigger down there. Right. So, if our trigger is at 2 times VCC over 3, we were charging towards VCC. Okay, and our starting off point was VCC over 3. And if we are charging towards VCC, our time constant is RA plus RB and C. Okay, because this capacitor is charging with both of these resistors in series, and this is high impedance, so we don't really care what is at this transistor here, and the inputs of these comparators is also infinite. So C RA plus RB. Okay, so that is our time constant for being high. Okay, so getting time high alone, we get RA plus RB times C ln of 2. So our time spent high is 0.69 multiplied by our time constant. Our time spent low is when we are ending up here at VCC over 3, charging towards 0, but we started from 2 times VCC over 3. Okay, so that's our endpoint. That is the goal. That is where we started. Okay, and when we're doing this, our capacitor is discharging through this transistor right here. So the path is only RB and C. Right, so our time constant is RBC ln 2, so 0.69 RBC. So the frequency of this is when the two times or the two periods added to one another. So it's 0.69 RA plus 2 times RB C, and frequency is 1 over F. Frequency is 1 over T. Sorry. Then, since we have two different resistors, these two times differ from one another. So we can have a duty cycle for our output. Now, duty cycle is the time spent high and the time spent low as percentages. Okay, so typically the time spent high is important. So if we take these and we plug it into this equation, we get RA plus RB over RA plus 2 times RB. Most of the time for oscillator you want a 50% duty cycle, so the same amount of time on as off. For this you need to choose RB much greater as RA. Okay, so that is one condition, and our duty cycle can never be less than 50% for this trip 5 timer. If you want something less than 50%, you need to invert the output somehow. Right, so we looked at this. The next point is to design and simulate two of these circuits. So, first one, design and simulate the monostable to create a 1.1 second pulse. You have a 100 microfarad capacitor available to you. And the second design is to design a 1 Hz astable with a 50% duty cycle, and you have a 22 microfarad capacitor available. Then lastly, I want you to redesign the astable to have a 75% duty cycle. So pause the video and see if you can come up with solutions. So the solution for the monostable is quite easy. Since our period is 1.1 times RC and we want 1.1 seconds, if we have a 100 microfarad capacitor available, the resistor we need is only 10 kilo ohms. To design a monostable for trip 5 is probably one of the easiest things to do. Okay, for a 50% duty cycle astable, we have the high, the low, the duty cycle, and the frequency equations available to us. Right, so for a 50% duty cycle, we want our time high and our time low to be approximately the same. So let's start with a time low equation and say that that is 500 milliseconds. So if we want 1 second, or 1 hertz astable, our period will also be 1 second. So with 22 microfarad capacitor available, resistor B will be 53 kilo ohms. Okay. Now, to make our astable with a 50% duty cycle, we need to choose our RB much greater than our RA value. So, let's choose it 1 kilo ohm. 53K is much greater than 1K. And your design is done. Okay, but I like to do some checks and recalculate the duty cycle. So our duty cycle is at 50.7 with a 1 kilo ohm resistor, and our period is 1.017 seconds with our component choices. Okay, it's always good to make sure that you did everything correct and that the component choices, especially when you're making assumptions, is not shooting yourself in the foot. Right. The 75% duty cycle astable, we're going to use all our equations. Okay, so the duty cycle is 0.75. This means our time spent low is 250 milliseconds and our time high is 750 milliseconds. So, solving these two equations simultaneously, you will get 18K and 33 kilo ohms. Recalculating the duty cycle, that's very close to 75%, and that is very close to 1 second. Okay, let's jump into the simulations and see if we did everything right. Okay, here I have my monostable set up. Capacitor, 10K, run it. We can look at our trigger. I set my trigger up for 100 milliseconds. And measuring the output, it goes high right after the trigger for roughly 1.1 seconds. So we can quickly get our measuring here, and 1.1036 seconds. So that is very, very close. Let's look at the only other place that we can look at, and right there. The moment we triggered, the capacitor started charging until it reached 10 volts, and 10 volts is a third of our VCC voltage, which is 15. So our monostable is working fine. Alright, let's jump over to the 50% duty cycle astable. So here is my astable build. Trigger and threshold connected together. Discharge on top of RB here. 1 kilo ohm and 53 kilo ohms. And 22 microfarad capacitor. Let's run this. Let's check our output. And this seems to be running at 1 hertz. Want to make sure. Can do a FFT. And that is at 1 hertz. Okay, looking at the capacitor charging and discharging, it's running between 5 volts and 10 volts. Between the threshold and the trigger. And the discharge is showing us the same almost as the output. Okay, and that is our 50% duty cycle. Here is my 75% duty cycle. If we run this and check out the output, let's increase this. That's 16. Let's make this -1. Okay, so it is spending a lot of time on and a little bit of time off. And we can check out FFT. The frequency is still at 1 Hertz. This is a bit flattened because that is seen as a lower frequency and this is seen as a higher frequency. But in any case, the fundamental here is still 1 Hertz. So let's get our measuring out. And 1.052 seconds. We can also check our time spent low. That is 275 milliseconds. And the time spent high, 777 milliseconds. So we achieved our duty cycle, we achieved our frequency, and that is it for the Trip 5 timer video. Thank you for watching.